When you play with a box of LEGO bricks, each brick is a small fixed piece. Imagine trying to build a tower by picking up each brick one by one and putting it on the table. That is a bit like using a Python list. You can store many things, but each piece is handled separately, and the computer has to keep checking what type each piece is, where it lives, and how big it is. NumPy arrays are like a tray that holds a whole wall of identical LEGO bricks at once. All bricks have the same shape and color, the same data type, so the computer can store them in one clean block of memory. This makes it much faster to perform the same operation on many bricks, such as coloring them all blue or counting them, because the computer can work on the whole block together instead of looking at each brick one by one. In short, NumPy arrays replace lists when you need speed and uniformity, especially for math-heavy tasks like image processing, scientific simulations, or machine learning. Lists are flexible but slower for large numeric data. Arrays are uniform, stored contiguously, and enable vectorized operations. The speed gain can be dozens to hundreds of times for big data sets. Explanation: creating a NumPy array is like filling a tray with Lego bricks in different ways. From Python sequences: if you already have a list of numbers, np.array of 1, 2, 3 copies those numbers into the tray. The list can be nested to create a grid. For example, np.array of 1, 2, 3, 4 makes a 2 by 2 board. Arrange: think of a counting machine that spits out bricks one after another. np.arrange of 0, 10, 2 gives 0, 2, 4, 6, 8. It works like the built-in range but returns an array. Linspace: imagine you want to place bricks at equal distances between two walls. np.linspace of 0, 1, 5 returns 5 numbers evenly spaced from 0 to 1. 0.0, 0.25, 0.5, 0.75, 1.0. Random generators: for games you might need random tiles. np.random.rand of 3, 2 creates a 3 by 2 tray filled with random numbers between 0 and 1. Other functions like randint, normal, and choice give integers, normally distributed values or selections from a set. All these methods give you a ready-made NumPy array that you can start playing with immediately. Explanation: every NumPy array has 3 important identities: shape, dimensions, and d-type. Shape: think of the shape as the size of a rectangular playground. For a 1D array like bracket 1, 2, 3 bracket, the shape is 3 spots in a line. A 2D matrix bracket 1, 2 bracket, bracket 3, 4 bracket has shape 2 by 2, 2 rows and 2 columns. You can ask an array.shape. Dimensions: ndim, this tells you how many axes the playground has. The line has 1 dimension, the board has 2, a cube of data has 3, and so on. Access with array.ndim. Data type: d-type, all bricks in the tray must be the same kind. NumPy records this as a data type, int 32, float 64, bool, etc. Array.dtype shows it. You can force a type. NumPy.array bracket 1, 2, 3 bracket, d-type equals float 64 bracket. Understanding these 3 properties lets you know how the data is organized, how much memory it uses, and what operations are allowed. Mathematical note: if an array has shape m, n, it contains m times n elements, each of size of d-type bytes. Explanation: choosing the right Lego bricks from a tray is called indexing, slicing, and masking. 1. Indexing: pick a single brick. R bracket 2 bracket gets the third element, Python counts from 0. For 2D, you can use R bracket 1, 0 bracket to fetch the element in the second row, first column. 2. Slicing: take a whole stretch of bricks. R bracket 1, 4 bracket gives elements 1, 2, and 3. In 2D, R bracket 0, 2, 1, 3 bracket extracts the first 2 rows and columns 1 to 2, forming a submatrix. 3. Boolean masking: pretend you have a checklist that says which bricks are red. Mask equals R greater than 5 creates a Boolean array like false, true, false. Using the mask, R bracket mask bracket returns only the numbers greater than 5. These tools let you grab exactly the data you need, just like reaching into a specific pocket of a toolbox. Example: import NumPy as np. R equals numpy.array open bracket 10, 20, 30, 40, 50 close bracket. Print open bracket R bracket 1, 4 bracket close bracket returns 20, 30, 4. Print open bracket R bracket percent 20 equals 0 bracket close bracket returns 2040. A vectorized computation is like telling a whole group of kids to add 2 to every number on their board at the same time instead of going one by one. NumPy's universal functions, ufuncs, are built in fast helpers that do exactly that. Example: adding two arrays. A equals NumPy array 1, 2, 3. B equals NumPy array 4, 5, 6. C equals a plus B element-wise addition yields 5, 7, 9. The plus operator is a ufunc that adds each matching pair. Other common ufuncs. NumPy square root of x gives the square root of every element. NumPy exponential of x computes e to the x for each element. NumPy sine of x and NumPy log of x are trigonometric and logarithmic functions. Mathematical example. If you have a vector v of v sub 1, v sub 2 through v sub n, and want to compute the Euclidean norm v norm equals square root of the sum from I equals 1 to n of v sub I squared, you can write norm equals NumPy square root of NumPy sum of v squared. All operations happen in C under the hood, so they are far faster than a Python for loop. The key idea: operate on whole arrays at once, not element by element. Imagine you have 100 stickers, and you want to turn every sticker upside down. With a loop you would flip each one individually, which takes time. With vectorization you ask the whole sheet to flip instant. Broadcasting is like having two trays of different sizes, but still being able to play a game together by automatically copying the smaller tray to match the bigger one. Rules: 1. Align the shapes from the rightmost dimension. 2. If dimensions are equal, they are compatible. 3. If one dimension is 1, NumPy pretends it is repeated to match the other size. 4. If neither condition holds, broadcasting fails. Example 1. Adding a scalar to a vector. R equals NumPy array with elements 1, 2, 3, shape 3. Scalar equals 5, shape scalar. Result equals r plus scalar. NumPy treats scalar as 1 and repeats it, resulting in 6, 7, 8. Example 2. Adding a column vector to a matrix. A equals NumPy arrange 9 reshaped to 3 by 3, shape 3 by 3. B equals NumPy array with elements 10, 20, 30, shape 3. B is treated as 1 by 3 and broadcast to 3 by 3. C equals A plus B. C becomes a matrix with rows 10, 11, 12, 13, 14, 15, 16, 17, 18. Mathematically, broadcasting implements the equation C sub ij equals a sub ij plus B sub j, where B sub j is virtually copied down each row. If you try to add arrays with shapes 2 by 3 and 3, you get an error because the first dimension 2 versus 1 does not match and is not 1. Broadcasting lets you write concise code without explicit loops or tile operations. Child analogy: you have a single candy, a scalar, and a row of 5 friends, a vector. Instead of handing the candy to each friend one at a time, you imagine that the candy magically appears in front of every friend at once. Aggregation functions reduce many numbers down to a single summary value, much like counting how many red bricks you have in a whole box. Common reductions: np.sum of r adds all elements. np.mean of r average, sum of xi divided by n. np.std of r standard deviation measuring spread. np.min of r and np.max of r smallest and largest values. When the array has more than one dimension, you can tell NumPy which axis to collapse. M equals np.array of 1, 2, 3, 4, 5, 6, shape 2 by 3. np.sum of m axis 0 sums down columns equals 5, 7, 9. np.sum of m axis 1 sums across rows equals 6, 15. Axis 0 works like adding up each column vertical. Axis 1 adds each row horizontal. Mathematical example variance. var equals np.mean of open parenthesis x minus np.mean of x close parenthesis squared. Here np.mean first finds the average, then we compute squared deviations and finally take the mean again. These operations are fast because they are implemented in compiled code and run over the contiguous memory block. Child analogy: imagine you have a basket of apples. Sum tells you the total weight, min tells you the lightest apple, and mean tells you the average weight of an apple. Explanation: Sometimes you need to reshape a tray of bricks, stick two trays together, or cut one tray into smaller pieces. Reshape, change the view without moving bricks. Our Reshape 2-3 turns a flat 6-element array into a 2x3 matrix. The total number of elements must stay the same. Stacking, put trays on top of each other. NPV stack, a B stacks vertically rows. Both arrays must have the same number of columns. NPH stack, a B stacks horizontally columns. Both arrays must have the same number of rows. NPD stack stacks along a new depth dimension. Splitting, cut a tray into pieces. NP split R3 divides an array into 3 equal parts along the first axis. NPH split and NPV split horizontally or vertically. R equals NumPy Arrange 12, producing the array 0, 1, 2 up to 11. Mat equals R Reshape 3, 4, creating a matrix with 3 rows and 4 columns. Upper comma lower equals NumPy V split Mat 2, splitting the matrix vertically into 2 sub-matrices. The first has 2 rows and the second has 1 row. The shapes become 2x4 and 1x4. These tools let you reorganize data to match the shape required by algorithms. For example, feeding a 2-dimensional image into a neural network that expects batches shaped batch, height, width, channels. Child analogy, Reshape is like taking a long line of Lego bricks and arranging them into a rectangle without breaking any brick. Stacking is like putting 2 rectangles on top of each other to make a taller block. Splitting is like cutting a big chocolate bar into smaller squares. NumPy stores array data in contiguous memory, meaning all bricks sit next to each other without gaps, much like a tightly packed bookshelf. Strides describe how many bytes you need to jump to move one step along each dimension. For a C-order array, row major, the stride for the last axis is the size of one element, and the stride for earlier axes is the product of the sizes of later axes. Example, a float 64 array of shape 3x4. Each element is 8 bytes. Stride for axis 1 columns equals 8 bytes. Stride for axis 0 rows equals 4 times 8 equals 32 bytes. This tells NumPy that to go from element R00 to R10, it must skip 32 bytes, 4 columns. Contiguity matters for speed. CPU caches work best when data is laid out in a straight line. Operations that can walk through memory sequentially are many times faster than those that hop around. Views versus copies. Slicing often creates a view, a different shape that shares the same underlying memory. Modifying the view changes the original array, saving both memory and time. Performance tip: prefer vectorized ufuncs and avoid Python loops. If you need a non-contiguous operation, consider NP as contiguous array to make a copy that is laid out in memory for optimal speed. Child analogy: think of a row of houses elements on a street. If every house is next to the next, the mail carrier can deliver letters quickly by walking straight. If houses were scattered with gaps, the carrier would waste time stepping over empty lots. NumPy arrays are the common language that many scientific Python libraries speak, so they can easily share data with pandas and SciPy. Pandas data frames often store their columns as NumPy arrays. You can get the underlying array with df.values or df.to_numpy. Changing the NumPy array will reflect in the data frame if it is a view. Create a data frame called df from pandas with a column named containing the values 1, 2, 3. Then assign r to the NumPy array of column A by calling df bracket a bracket to _numpy. Multiply r by 10, which modifies the data frame column as well. SciPy functions, for example linear algebra, sparse matrices, and signal processing, accept NumPy arrays directly. No conversion is needed, which keeps the workflow fast. Zero copy interoperability. Using NumPy end-array memory buffers, you can pass data to C or C++ extensions or to libraries like Torch, which is PyTorch without copying via the array interface protocol. Import the solve function from SciPy linalg. Define matrix A as a NumPy array containing rows 3, 2, and 1, 4. Define vector B as a NumPy array containing 5 and 6. Compute X by calling solve with arguments A and B, which returns a NumPy array with the solution. Data type consistency. When moving data between pandas and NumPy, keep an eye on dtype. Pandas may use object dtype for mixed types, which loses the performance benefit of NumPy. By treating NumPy arrays as the backbone, You can seamlessly move from data cleaning with pandas to heavy numerical work with SciPy without rewriting or copying data. Child analogy, think of NumPy as a universal Lego brick. Pandas builds houses with those bricks and SciPy builds bridges. Because they all use the same bricks, you can pick a piece from a house and use it instantly to build a bridge.